Just jump in very quickly, gonna kind of go back over. Just real quick, 6.4, 6.5, then we'll jump into 6.1 and finish up today. Alrighty, finding value of the normal distributed random variable. Okay, let's remember on this one right here in 6.4, like I said, we go through this super quick, just so you can kind of remember how this was done. On this one, remember what it was saying was this. It's saying, hey, it's going to give you the area, but it doesn't give you the z-score. Okay, so remember on this one, you can either A, use your table in your book, or B, use your calculator, which is going to be your inverse norm, which is just fine. But you do need to remember that your calculator will only take the area to the left. Okay, so you just kind of have to be cognizant of that whenever you're doing it. Okay, but what is nice is remember, if it does give you area to the right, let me draw in here so everybody can see. If for some reason it said, hey, they gave you this area here, well, let's remember, you can just do 1 minus that because it doesn't really matter, because that z-score is going to be exactly the same, no matter if you're taking area to the right or area to the left. That's still going to be your point. Okay, so just kind of remember that. I think we showed some other ones here. There's how you find it on the table. Notice this will be 0.63. Z-scores are always rounded to 2 decimal places. Remember, your area is always rounded to 4 decimal places. If it helps, area is probability. Okay, probability is always to 4 decimal places. Notice this one here says 0.996 to the right, which is asking for that. So for you, you could come in here and do the 1 minus 0.0096, find the area to the other side, and do that. Does that everybody remember that okay? Oh. There we go. It was not showing me. I'd be happy with no way to show me. If I could turn that off, I would. Teaching ITV in the summer. Let's see if I can't turn that off. Don't feel bad about yourself. Watch your gut all day long when you're trying to edit these videos. Okay. They're like, the camera adds 10 pounds. It added 50. Me, okay. So, and there you go. Once again, like I said, use it however you want. If you want to use your table, I'm all for that. Whenever you do your final, I will be giving you a list. Okay, it'll have a whole bunch of formulas. It'll have your tables. So if you decide to use that, feel free. Okay. Once again, area to the left. That's what you're just going to kind of have to keep up with right there. Is it looking to the left? Is it looking to the right? Be careful on some of these. I think it was this one. Yes. That's the one that, remember, kind of let y'all play with a little bit. Look at the geometry of it. Okay. Notice they're just saying this one here, and then the lines between. And this is where your pictures are going to help. Even if you don't do a great picture, you can say, hey, I'm looking for this, and I'm looking for this, and I know I have a mean right here. Okay. And so it's saying this total area is 0.8864. And then, like I said, just use your process of deduction. You're all really good math students. Okay. You know, halfway would be 0.5 because half of that being filled in is 0.5. So that's why we kind of did that empirical rule thing. Kind of helps you out a little bit. Okay. To kind of have an idea how this thing is and why we like the symmetry of a normal curve. Okay. And that right there was 6.4. So that helps you out. If you haven't done your homework yet, kind of good little review. Like I said, very quickly, we'll look at 6.5. 6.5, remember the hardest part about 6.5 was obviously, probably for you, is going to be remembering the more than, less than, and what is it supposed to look like. This is the part where we start doing that continuity correction. Okay. You are here, remember, continuity correction is that little plus or minus, okay? And when you're dealing with, hear my words, continuity correction, it's always 0.5, always, okay? Later on, we're gonna get into something called margin of error. We can change that. The continuity correction is always 0.5. As a review for this one, remember it comes with some rules. They have to have a fixed number of trials. They have to be independent. Remember what we said was independent. Independent means the probability of this one doesn't affect the probability of the next thing. Each trial, two possible outcomes, success and failure. Remember how we define that. There is a probability for success, and then there's a probability for failure. The failure is the complement, 1 minus p. And then we're still doing a binomial random variable x, that p of x equals x, or p of x is less than whatever. And then they gave us the sigma down here, but they gave us sigma squared, but obviously if you wanted to find sigma, you just take the square root of all that, and there it is right there. Because remember, when you have variance to get the standard deviation, you just take square root, okay? So really overall, as you can tell so far, not super hard math in this class. It's just kind of the remembering what and when to use it. Sometimes your thing has a button on your calculator. Sometimes you got to do some very easy formulas, okay? Good news is you don't really have to remember formulas. I'm going to give you a formula sheet for your final, but I'm not going to name the formula. So you're going to have to remember, oh, wait a minute, hold on, this one says this, okay? But that is the formula, okay? Gave you this right here. We got a memory booster, but there, biggest thing to remember on this one, we won't be using this one a lot during this part, okay? But it says, hey, we're using this one, that binomial, but when things are less than a certain amount, okay? Well, anything less than 10, we can use this guy. Remember that binom CDF, binom PDF, okay? If you go back and look at your question on your midterm, I think the real estate question, it says something like, hey, 14 houses and stuff like that. The probability is like 60%. Well, realize the 60% of 14 is less than 10. And so you couldn't use what you're going to use in this one. You would have to use that binom CDF, okay? You're not going to have a question like that one on the final. I don't pull a cumulative, okay? So everything now is going to be this, okay? But I will say this, on Hawk's homework, they may try to test you. They may say, hey, here's a scenario, okay? And you need to work out the NP, is that greater than 10? Is the N 1 minus P, is that greater than 10? If it fails on either one of those, can't do it, okay? And you can just, whatever button they tell you to push, move on with your life, okay? So kind of keep an eye for that. I am benevolent in the sense of I won't do that to you on a final, okay? I'm gonna show you right now, everything on the final works, okay? I'm giving you just enough trials, everything's gonna work, okay? Continuity correction, here it is right there. Continuity correction for this one, remember, is going to be this right here. Just kind of get through it very quickly. It's that little interval, that plus or minus from the data point. Okay, they give you a mean, that's your N times P. Okay, you have to work it out anyway. Then they're going to give you a standard deviation. Okay, we'll get into that one a little bit later. But still, for right here, that data point plus or minus. So this continuity correction, remember, it's going to be data plus or minus 0.5. And like I said, the hardest part on some of these, if you'll notice that this one says right here, let me get to it. Is at least 2 people. Okay, notice that word at least. Notice this is on your calculator. How would you find the area? Do you remember the button, how you find the area under the curve? Because you don't be sitting here trying to do calculus. Think about it. Start to the end.
Second bars. Yes.
Second bars, yeah, you gotta get to, just give me the button.
Inverse norm.
Normal. Inverse norm, good question. Inverse norm finds you the z-score if they give you the area. If they just give you the Z-score, normal CDF, okay, is how you would find the area. Okay, I think it's number 2. Is it number 2 on your calculator? Because I think number 3 is inverse norm.
Yeah.
After you go to second, VARs, remember VARs is actually your distribution after you hit the second key, okay? And so it'd be the number 2. And the reason you think about this continuity correction is for one simple reason. Think about it. This right here is deciding where is going to be your lower bound, where is going to be your upper, and then your mean and your sigma, okay? So you can't start this for now, you can't start your data at 2. Because of that continuity correction, you have to back it up to that 1.5 and let that be your lower bound. And do we remember what we were using for our upper bound on this one? 1E99 or some really, really large number. Okay, you can test it out with like using like 10 million or even 20,000. My computer, my calculator doesn't do that, so I started using the 1E. Never have a problem. Okay, so it kind of helps you remember if you're going to negative infinity, remember do negative 1e to the 99. If you're going to shoot off to positive infinity, go 1e to the 99. Just kind of help you out and remember that. And then in your book and on these notes, you have this right here. Okay, and updated notes will be loaded up tomorrow, Saturday at the latest. I have a lot of stuff happening tomorrow. But remember, it said, remember the word at least? Okay, well, if you look at this one, look what it says. At least, there's the data point they're giving me. I know from 45, I'm gonna go plus or minus 0.5, which means I'm gonna back up to 44.5 or move forward to 45.5. And what does this one tell me? Oh, look, when it's at least, your lower bound is going to be your 45 minus the 0.5. So there's where your lower bound has moved to. Okay. And so I just kind of kept those around me until I got used to them. Okay. Those will not be on, I will not give you these, just so you know. Okay. Those I don't provide. And there's just some rules again, like I said, all in your notes. And then we just did we did a bunch of examples. So pretty good. Feel kind of caught up a little bit. Okay, let's jump in now to 7.1. All right, 7.1. Okay. I would have to say it's probably one of the more abstract lessons you're gonna have. Because while you will, in that last chapter, you're gonna have some homework problems that involve themselves. You could even, technically speaking, do some very mild statistics with it. It would kind of work for you, okay? And it is doable, okay? I did say at the very beginning of chapter 6, it's more conceptual. It still really is because everything's still kind of exacting until we get to that continuity correction. By the way, it does bear worth mentioning. The reason for that continuity correction is because we've gone beyond discrete and we've gone to continuous. We've made that transition over, okay? Even though you could say, because I think one of your examples I used was like flipping a coin 1,000 times. Yeah, you can count it, but that would be annoying. Okay, so that's why we switch it over to continuous. Okay. Well, I want to set this story up correctly because I do genuinely, I get it. You know what? After the final, I half expect most of you to do this. You're gonna put your pen down, turn off the computer, and be like, I'm done. Take all this, flush it down the toilet. Totally understand that. Okay, but I would hope to think that something's gonna stick a little bit. That's what I want. You know what, the math's out there. You can learn it again really quick if you ever become a statistician later on. Or you work for the schools and they hand you, they did it to my wife just last week. Here's how your kids are doing compared to everyone else. Okay, and it was a normal curve. Okay, and I was up there with her and all of a sudden, you know, she goes, hey, how would you translate this as somebody who teaches stats, not to what they tell us? And I explained it to her and her little co-teachers, and they're like, okay, that makes a lot of sense. Okay, and it helped. Well, now you can be that person later on, whenever you're doing whatever job, because every job out there, I don't care what you're gonna be. Somewhere woven in there is some sort of statistic or something, okay? Now, I showed you that Gaussian board. Remember the little dots that fell down and we pretended they were trials? And things tended to always flow toward a normal curve, okay? That is still true. And the reason that is true is because what you're going to start learning today, okay? It's called the central limit theorem, okay? You're never going to do this in statistics. You're never going to use specifically the central limit theorem, but this is going to be as close as I can get you to doing a mathematical proof in this class, okay? What it tells you is, hey, how come this works and how can we trust it? That kind of makes sense. Like, how do you know you can trust these statistics whenever you take them or when you see them? How do you know? It's because of this. Okay, so let me show you what it actually is. We're making a slow transition now over the next few chapters. Okay, not chapters, sorry, units, 7.1, 7.2, and stuff like that. From concrete population, here we go, to now we're going to start taking samples. We're making that transition, okay? If, for some reason, I knew everything about a population. I mean, we're talking everything. I'm not talking samples. Everything about a population. I could easily have a graph that looks like that. Can we all agree? If I graph everything in a population, I could also have that, or that, or that. Tell me something though. What's the problem with those? From what you've learned now, post midterm, what do you see as the problem with any of those? Use the knowledge that you've gotten. Ask yourself, okay, how would you take a standard deviation? You could probably find a mean, right? But how would you do the standard? Because doesn't standard rely on what? Some sort of symmetry, right? Do you see any real symmetry with these? Even the last one, while it looks partially symmetrical, is it? No, there's nothing symmetrical about those. And so there's nothing I can actually say, well, how do I find out anything now? Because we have that empirical rule, not empirical suggestion, not empirical, no, empirical rule that says if I have a mean and I go one standard deviation away, most of my data should be within 68%. If I go two, what is it? 95, very good. And then if I go three, it's 99.7. So notice I couldn't do that with this. I can't come up here and go, well, that's my mean. But look, if I go one standard deviation away from that one, can we agree that 68% of my data fits in there? I don't know. Got a pretty big outlier in one direction because that one's skewed. Okay. Well, then how can we trust anything then? If the real world, when you do populations, does not create a normal curve, then what do? That's why we have the central limit theorem. Okay. And this is what I'm gonna be explaining the whole class. But I'm gonna kind of like tell you the end right now. Okay, I'd be a horrible public speaker. Okay. The end is this. If you take enough samples from the population, isn't that what you're doing in a statistics class, really? Taking samples. If you take a large enough sample, it always becomes a normal. Always. Okay. It's hard to prove that, except if you go back and look at that Gaussian board I showed y'all. All of those little samples that were falling, right? Well, what happened? It turned into that little normal curve. Okay. Nature tends toward a normal curve. Now, does that mean that's the only thing we got? No. There are other distributions out there. You're going to learn about one. You're going to learn about a chi distribution. Okay, there's F distributions, there's a T distribution that we'll also learn about in this class, okay? And there's a few other ones, but the big one, like, I mean, I'm talking like A number one used 90% of the time, a normal curve, okay? Because it works. It works reliably well, okay? So what does that mean? Well, that just means that you're gonna have a little bit more terminology here. So let's kind of keep going with this. Sampling distribution, the distribution of the values of a particular sample statistic, okay, for all possible samples of a given size. And then, of course, we kind of keep continuing here, the sampling distribution of sample means, the distribution of sample means for all possible samples of a given size. N. Well, that's just a bunch of words salad if you don't know what it's saying. Okay, let me tell you what this says. Here is a number of roles. Okay. Now, obviously, it's not all the roles I could possibly do, but hopefully every single one of you in here, because every single one of you passed your midterm, you should be able to tell me what type of graph that is. Very good, uniform. Notice it comes in here pretty straight, never perfect, right? Now, why is it not perfect yet? We're always reviewing this class. Why is it not perfectly uniform yet? Right now, my N is 300. What's going to happen to this graph if I make N 500?
Be closely uniform together.
They're going to get closer, aren't they? If N goes to 1,000, closer. N goes to 1,000,000, even closer. And eventually they're going to get so close, it's just going to be a straight line all the way across, right? Because what? That law of large numbers is things kind of just tick, 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 tick. The law of large numbers goes up. Okay, so having said that, let's remember you have ways to figure stuff out. Okay, if you put this in your calculator, if I told you N is 300, you could find the mean of this. The mean would be 3.5. Standard deviation, okay, 1.7. I think it's 1.70. Okay. Do all that in your list function in your calculator, right? Or use Excel. I don't care. Okay. Now, that's my population right now. I want you to realize that we're dealing with populations right now. That's everything. That's all my trials, whatever now. That would be something I could use. Now, I could take samples from that, right? If I wanted to. Show you how this works. First off, you need to start remembering some new. If you can't see that, let me rewrite a little bit bigger. Look what this says. Remember, this is not going to be your eventual terminology. Right now, we're doing what we call proof of concept of the central limit theorem. So they're going to give you some kind of wonky notation because I get some of you here may be looking at this going, that says mu. Mu means population. Why do they put an X bar with population? Because X bar says sample. Okay. It's because right now I'm showing you the central limit theorem, what it's saying. Okay. So mu is equal to X bar, sorry. Wrote that completely wrong, didn't I? Mu is X bar. Well, let me go and just give you the other one too. Let me give you your standard deviation so you can kind of see them bigger. Okay. Notice, good thing. This mu of X bar is the same thing as your mu. It's saying the sample of your population mean is the same as your population mean. So when I give you a mean, if they start saying the population mean is this, probably like on your homework, well, then what would the sample mean be? The population. They gave it to you. There it is. There's no sort of like, math to be done. You're literally matching it up, correlated right there. Okay. But there is a formula now for your standard deviation. Okay, your standard deviation has changed now. Write a little bit bigger for those in the back just in case. They're going to give you a standard deviation, or they're going to give you a variance, and then you just got to do what with it? Square root, exactly. Let's always remember that. Don't get hung up on the easy math. And then they're gonna give you some sample sizes. Okay? And then you just take the square root, and it's gonna give you a different type of square root. I mean, a different type of standard deviation. Okay? While you still probably don't understand exactly what this thing is saying yet, are you okay with the math? Because that's really, I mean, that's, you want to pass, so you're okay with the math so far, okay? The mean of X bar is the same thing as the mean, okay? Standard deviation, that's the formula, okay? And this formula keeps coming back. Okay, over and over and over again, from now on, this one's gonna keep coming back, okay? Because we're no longer dealing with population. After this chapter, we're done with populations. Population's pretty, okay? You know, it's not about population, there's really no math to be done. But you're in a statistics class. It's taken this long to teach you the basics before we can actually start doing statistics. Okay, and that's what we're about to start doing. We're gonna start doing statistics, we're gonna start taking samples. And remember, samples are not the same as the population. If I knew the population, I don't need statistics, I know everything. That's how come I have those pretty buttons on my calculator. Okay, statistics says this, hey, if he got some data and he does run some numbers, he's gonna get some answers. If I run the same data, but I take a different sample, our numbers aren't gonna match. They shouldn't match. They should be close. And then when these two do it, same thing's gonna happen. He does it, same thing happens. But then what we can start looking at is if enough people do enough samples, we can start looking and going, hey, they kind of match. There's some variance. We expect that. But they're all kind of clustered. And then if she does something and it's like way over here in left field, we can go, okay, we don't need to count that one. That's an outlier. That one probably, maybe she did something wrong, or maybe it is something we need to look at. Did she do something different that we need to look at? That's where statistics comes in. Okay, that kind of help y'all kind of see things a little bit. Okay. Let's go back to my example here. Notice, okay, I can take a sample of this. I want you to realize something. To do this, I didn't really do this. Okay, so no, my thumb would still be bleeding. Okay, somebody flipped a coin. And then they recorded their answer. Then they flipped a coin. Then they recorded their answer. They flipped a coin. Then they recorded their answer. And they kept doing that over and over and over and over and over again, okay? And they did it 300 times. And here is their results. Remember, each time they flipped the coin, that would have been a trial, correct? And that trial would have been listed on a sheet of paper. Trial number 1, I wrote a 4. Trial number 2, I rolled a 1. Trial number 3, I rolled another 1. Okay, you kind of get the hint. I can go in there as someone who wants to study this, because maybe I don't know the whole thing. And I can say, I want to take a sample. So I'm going to get that whole list of 300, and I'm going to do a random sample. It's going to just, a computer's going to randomly sample, say 40. Okay, so now I have a sample here, okay, of n. Remember, little n is always sample, big N is always, don't get used to seeing big N ever again, probably. Okay, so I take a sample of 40. Well, that's nice. Well, remember earlier I gave you a mean. Okay, the mean of this was what? 3.5, which we can now say, what's the mean of my sample? 3.5. Remember, the mean of the sample is the same as the mean of the population. Okay? My standard deviation, though, from earlier, dealing with my population here was this. We're just gonna use the 1.7. Like I said, I think it's 1.70, but we'll go with 1.7. So is that my standard deviation of my sample? No, because look, they're saying, hey, you can't use that standard deviation anymore. Before I even work it out, why?
Smaller part of what it was.
Thank you. That's perfect. That's a perfect way. And if you didn't hear that online, it's a smaller part than what it was. I'm no longer using n is equal to 300. I've taken a smaller sample size. Okay, remember some of your homework questions that said, hey, I'm showing you this normal distribution. Well, what's the mean now if I shrink it? What's the mean now if I move it? Well, that's why they were doing that. They were saying, hey, if I have a large sample size, I'm gonna have a pretty big, large normal distribution. But if I shrink it, but that mean never changes, well, now, since it shrank, what do you think is gonna happen to the standard deviation? Is it gonna get larger or is it gonna get smaller? Smaller, think about it. If I had this much and all of a sudden I do this, kind of help you out a little bit? Okay, that's exactly right. You put everything into your formula here. The standard deviation of my sample uses this formula here. I've been given all that information now. I've got this 1.7 divided by 40, which is nice because that becomes 0.27. So my new standard deviation is 0.27, which, okay. You might be thinking, who cares? Well, let's do another example just real quick, and you kind of see what you can work out from it. And then we'll go from there. I want you to work this one, so I'm gonna give you about 2 minutes. Probably less than that because it's super simple. Look at that guy right there. I give you all the formulas. Suppose that movie ticket prices in one area have a mean of $8.32 and a standard deviation of 0.72 or 72 cents. Ticket prices are recorded for the samples of 52 theaters. Calculate the mean of the resulting sample distribution. Hey, how easy would this be to do in Hobbs? All the theaters, 1. Used to be 2, we used to be ballers. Okay. Y'all remember the other theater that was here in town? Did y'all not? You know where the Thriftway's at? By the mall or the hall? There used to be a theater right behind that Thriftway, literally like 6 feet away, facing toward the wall. You had to walk down the side of Thriftway and walk into this theater. It was very weird. So, yeah. Hey, what's my mean?
$8.32.
Yeah, hard math on that one, huh? $8.32. But now give me a standard deviation. So my mean here, which is the mean of the X bar, is going to be the 832. Mean of X bar. What's my standard deviation they gave me?
Cents.
What's my sample size?
52.
What we got?
.0991.
0.1. Good. Okay. Now, let me show you what you just saw. Okay. Because I have that kind of time, I go to El Paso about every 3 weeks. And I decided to go to every single movie theater in town, all of them. Okay, remember, get it out of your head that population has to be this infinitely large number. You are a population of my statistics class 11702. You are a population. If I decide to start taking samples of you, that's a statistic. Okay, but you can be counted as a population. So in this scenario, there is obviously more than 52 theaters in this town. Okay, so this person went around and studied every single theater. Okay, and found a mean and found a standard deviation of the ticket prices. So they have a mean of 832. And then they have a standard deviation of 72 cents. So concrete, these are concrete numbers right here. Do you hear what I'm saying? Why am I saying concrete? How exacting are these numbers right here? I'm not gonna keep going. That is one standard deviation away, right, from the mean? How much information sits in there? How many of my movie theaters fit within that? Within those prices?
68%.
68%. That's exact. Why is it exact? Exact-ish, okay, let's always kind of go, but it's exact enough that you will never know the difference. Why is it exact? Population. You studied everything there is to know about it. This person, you went to every single movie theater. You got every single movie ticket. You looked up all the prices. You put them in Excel. It ran the numbers. It gave you a mean and it gave you a standard deviation. Okay, there you go. Pretty nice. That's what you've been doing, right? But guess what? Who has that kind of time? Who has that kind of money? So the question says this, hey, somebody, any one of you decide to go test this out and you go, okay, hey, I'm going to just go sample 52 out of the, who knows how many were there? It could be 10,000 theaters. I think I looked up, I think New York City, because we're going to be there in the Christmas. They have something like 48,000 movie theaters. 48,000. That's insane. Now, mind you, that's from little mom and pop all the way up to big movie theater. 48,000. And this person just took 52. Okay. Well, notice if you look at it this way, remember, this is conceptual. You still got a normal curve. And what the central limit theory is saying is, let's be honest, I don't know if my population actually creates a normal curve. It could create a logarithmic curve. It could be normal. Who knows? We don't really know what the population, what the curve of this thing actually looks like, right? But I can tell you this, that whenever I take a sampling of it, I've still got this 832, and I've still got one standard deviation away from that, which for this one right here, we'll go 822, and then we're going to go 842. That's still 68%. But this right here is my sample. And this is what I'm trying to get through to you today. I can now infer. Okay, infer. I don't know. Okay, if I was going to go to this city, whatever this city is, I take a sample, I can infer that if I go to this city, 68%, okay, of the ticket prices will be between this price and this price. And for me, what I'm looking at, I'm going to say between 822 and 842. I'm off. It's true. But I'm doing a sample. I don't know the population. Remember, if you know the population, you don't need statistics. Okay? But now, remember that word inference? This is why we call this inferential statistics. We can infer from the data we have gathered to say this. Okay? Now, we're going to get a lot more exacting as we go on and move forward in this class. This is just proof of concept right now. It's saying you take enough, if I take enough samples, like, can we all agree, like on my little dice rolling, I took a sample of 40, right? Could I take another sample? When I took another sample, would it be the same as the first sample I took? No. Could I take a third sample? How about a fourth? I couldn't?
Reduce every time, right?
No, remember, sample was okay, that's a good question. And I think that shows some misconception. When you take a sample, you're kind of doing this. You're that weird person at a party that like dips into the salsa bowl, tries it, and nope, and puts it back. Okay? Don't tell them I don't have parties. They're nasty people. No, you're literally taking a sample, you're like, okay, I have an idea what this is made out of, and you're putting it back in. Okay, so I can take a sample, pull it out, put it back in, take another sample, look at it. And then what's gonna happen is if I do that enough, sample, record it, sample, record it, sample, record it. That's going to approximate a normal curve. Okay? You don't have to take that many samples. That's why you're getting formulas. Someone did the math and went, hey, if I do this enough, this is what works. Look at this one. Let's go back. The central limit theorem says for any given population with a mean mu, you don't have to write this down. I'll just read it to you. This is just the proof of concept. And standard deviation, sigma. The shape of the sampling distribution of sample means will approach that of a normal distribution as the sample size increases. Okay? For this text, we will consider a sample size to be large enough if n is greater than 30. So that means you're going to take a sample, make sure you did it above 30. Last semester, whenever I made the students do a project, I said, make sure whatever data you get, hence their data was their population, make sure you have enough data that when we start taking samples, you can at least do 30 or more. Of course, when day one in class, when I'm describing that, they're like, why? You'll see later. And then the aha moment, when we got to 7-1, they all went, ah, that's why you told us this. Yes. Okay. Anything less than 30, you don't need it. Okay. It's not going to be as exact either. Okay. Or you'll use some other distribution. The larger the sample size, the better the normal distribution approximation will be. Kind of like that law of large numbers. Okay. So look at this one right here. Once again, I'm using this one for a reason, and I'm going to blow it up a little bit here. Let me show you something. This is my populations. Okay, my population, my N is 300, big N, right? Population. Then I decide to take an N, small n of 40. Okay, go with me on this. Because this is where you kind of lose people. Let me use y'all before I use this, because you can see each other. Here's all of you. I decided to just take a sample of 2. Here we go. Here's my sample. I look, I put them back. But then I keep him and I pick you. Okay? Then I pick you. Then I pick you. Then I pick you. Then I can, when I go through everybody, then I go, now I'll go to you. Can't pick him, so I picked him. Then I go to you. Notice how this is working? Kind of remember this a little bit. Maybe you should remember this. Remember the combinations. Remember, so many choose 2. And here I think there's 26 people. 26 choose 2. Well, look at this. I have 300 choose 40, which means I take a sample of 40, then I put it back, and I take another sample of 40. If I took all the possible samples that I could ever take, it would approximate a normal curve. Now, what's nice is you don't have to do that in anything. Even in statistics, we don't do that. We have formulas. Remember, this is all proof of concept. But I will tell you this, that if you decide to take all of the possible samples, okay, for this one, it would turn into 300 choose 40 of 9.793478923 times 10 to the 49. So that's basically 9. Move that decimal places over 49 places. And that's how many possible combinations are. And if you did that, there's your curve. I don't know about you. That's good enough for government work. It approximated a normal curve. And that's what we wanted. That's what the central limit says. It says, hey, if I do this, and kind of the central limit theory is telling you this in the background, going, I've already done it for you. So you just have to trust at this point that if you're doing a sample of a population, that, let's be honest, the curve may not be a normal distribution. It's probably not. Okay, when you're talking about a population. But when you take a sample size that's large enough, it's probably going to approximate a normal curve. If it doesn't, we've got other things. But like I said, 90% of the time, it's going to approximate a normal curve. If it doesn't, we've got a couple of other distributions we're going to use. Okay. Do you kind of get it now? Did everything kind of come full circle a little bit where you kind of go, okay, I kind of get it. You never do this in statistics, but this is sort of like, why does statistics work? Well, you need to know this or else you're going to walk into chapter 8 going, but it's not a normal curve. It's not, it can be. Why would you know? Or maybe you just don't even think about it. I wouldn't feel right letting you walk into this not realizing that. Okay, it's conceptual. It is the basis of statistics. Okay, one of the concrete foundations. One of. There's a bunch of pillars, but one of. So, having said that, what does that mean? Well, let's go back over this real quick, just so you remember. Remember this, mu is the same thing as the mean of the X bar, or the sample mean. The standard deviation of the sample of X bar is the formula there. A normal distribution may be used to approximate a sampling distribution of sample means if either of these are true. One, the sample size is at least 30, or they tell you, hey, the population is normally distributed. And I do not know this, and I need to find out. And I'm not talking bad about anything. So somebody runs off or if they hear it on camera, they're like, he's talking bad about the schools. No, I'm not. I want to find out if their data, because I did look at data for my wife and they showed a normal distribution. Well, is it really normally distributed? Is their population that they're comparing what my wife's numbers, is that really normally distributed? Or, to kind of get down to the nuts and bolts of it. It's good to ask questions, right? Be nice to know. Because if not, then, okay, did you take a sample over here of your students? Well, that would be normally distributed because you're using more than 30, and then you take them, but then you're using my wife's population. How did hers become normally distributed? Notice some of these little questions I want to ask at times, so. But then I usually get told, shut up and go back to the college. Okay. So that's all you need. One of them. One, if they tell you, hey, this population you're studying, we looked at it, it's normally distributed. Sweet, which a lot of things are actually normally distributed. Like, remember when I showed you all the heights of people like in the United States? That was a normal distribution, it worked, okay? But if it's not normally distributed, just know, take a large enough sample size, it's gonna be normally distributed for you, okay? So what's nice, the central limit there says this. If you have populations that look like that, okay, and you think to yourself, well, there's nothing I can do. Well, yeah, there is. You can come in here very easily and just say, hey, if I take a large enough sample, look what happens to the data. It's always going to approach a normal curve. Remember, approach a normal curve. Nothing is perfect in statistics. But man, it's pretty close. It really is. If you're doing good sampling, good proper sampling, if you're doing the math correctly, okay, it's gonna be pretty exact. And the better the data you have, the more exact it's gonna be. Okay, so in this class, pretty soon, we're gonna start learning about that continuity correction a little bit more. We're gonna change it to margin of error. But we're also gonna notice that you're gonna start taking samples, okay? And I say this because I want to preface everything for you as we kind of get to it, because like I said, and I've warned since the day before we started taking this classes, things get abstract after the midterm. Things get a little bit more just like, I get the math, but man, what is it saying? Okay, because I will ask you on your final, don't just give me a number. What is it saying? What is this saying right now? Okay, and I want you to have that concept because it is one, it's an answer. Okay, what is this telling you? Okay, well, it's saying this. No, what is it really saying? Okay, one of the things you're going to learn is, and I brought this up, how many of you watched the last election and how many of you heard, okay, maybe you heard the last election, not watched it, and they said something like, we sampled 1,000 people in New Mexico. Okay, and this many people are gonna vote for whoever, or this many people decided this. Have you ever had somebody say it to you, go, well, that's not enough of a sample? Have you ever heard somebody say that? They go, that's not big enough. They don't know what they're talking about. How do you know? How do you really know that's not a big enough sample? Did you do the math on it? Did your friend do the math on it? Or they just think it? Believe it or not, you'd be surprised how small of a sample I actually need to find out about a population. Okay, confidently find out a population, and in actuality, you would think that the larger the sample size, the better your answer would be, don't you think? Complete falsehood. Sometimes the bigger the sample size, the more your data is gonna lie to you. You're gonna learn that. So notice some things you can take away from this class. So later on, you can go, when you're 4 years down the road and there's another election happening, you can go, well, they didn't take enough people. You can go, wait a minute. Wait a minute. I remember something's gonna tickle the back of your head and go, how do I know? You're gonna have that knowledge. Okay? Let's do an example real quick. A couple of examples here. Decide if this statement is true or false. Please tell me. A sampling distribution of sample means has a mean mu equal to the population mean mu divided by the square root of the sample size. Is that true or false?
False.
False. That's not it at all. The sample mean is equal to what?
Population mean.
And nothing more. That's it. Okay, don't let them fool you. You're smarter than that. Hard math on this one. Find the mean of the sampling distribution of the sample means using the given information. Round your answer to one decimal place if necessary. Please tell me the formula I need to use for this one. There you are. That's it. X bar equals mu. So what's my answer? 69 exactly. Because once again, the mu of X bar is equal to the mu and vice versa. So notice no math at all. Boy, such hard homework. I don't give you all hard enough homework. Boy, that wasn't go to hell, folks. I'm just joking. I'm not changing the homework. No. Do this one. I gotta remove those. I hate those. I don't mind transitions in my main PowerPoint. When I get to the homework questions, I don't like the transition. They annoy me. Do this one real fast. Tell me what you can find. See what it is. Find the standard deviation of the sampling distribution of sample means. Here, I'll even be nice to you because you might not have it wrote down. Remember, to find the standard deviation, you're looking, of X bar. You look for the standard deviation divided by the square root of n. Don't break the calculator for me. Did they give you enough information to find it?
Yeah.
Yeah.
1.6. 6.
0.6?
1.
Oh, 1.6. Round to, let's see, 1 decimal. Yes, I think I did 2 in your, I need to start reading my questions. 1.6. Remember on this one right here, you're just going to be putting in that 14 divided by what? Square root of 81 or 9. They're not always that nice to give you those nice, pretty numbers, are they? Do 2 more and then we'll be done. A study on the latest fad diet claimed that the amount of weight loss by all the people, hence that word, all. They're telling you right now, and this might be a little hint for your final. They're giving you all. They're saying, hey, I'm going to give you everything, and then I'm going to change it. The weight loss by all people on this diet had a mean of 22 pounds and a standard deviation of 5.4. That first question says, hey, what's your mean? What's the mean of the sample?
22.
22. It's always the mean of the population. The mean doesn't change. Okay. So this is the same as this, which is 22.0 pounds. Very good. What do you think the next thing they're going to ask for?
Deviation.
Standard deviation, exactly. So standard deviation of X bar is equal to the standard deviation divided by N. Which is equal to, well, they give us a standard deviation of 5.4, and then they give us a square root of 77, and then they tell you to round to 2 decimal places.
0.62.
Very good. 0.62. Now, one question I want to ask you, did they give you enough of a sample? Was your sample adequately large enough? Did any of you even think about looking at it?
That's just beautiful 30, right?
Exactly. Got to be 30 or greater. 77 is perfect. Okay, so just be real careful about that. Did they ask you for a probability? No. Notice the difference between this one and the binomial one you just learned. Okay, that one was asking for probabilities looking. Okay, so notice a little bit of a difference in there. Okay. Before we continue on, let me try to, I am racking my brain because there's something I wanted to tell you that's coming up. And I'm probably gonna forget all about it. It's gonna be very important, and I'm gonna get this a nasty email. No, I'm just joking, it's not that important. We're gonna keep continuing on 7.1. I think it only goes to 7.3 on this one. Okay, and then we'll jump in. I would suggest trying to get ahead. If you can possibly get ahead, get ahead. If things start getting weird for you, I'm receiving either A, I am just that awesome of a professor, which I'll take it. I'll totally own that. I am an award winning. So, no, I'm not receiving a bunch of email. Okay, which is totally fine, trust me. Okay with that, no. If you're having trouble, don't struggle alone. I'm here to help you. Send me an email. When you do, please send me a screenshot though, because if some of you, the emails I have gotten, some people say, well, it's question 3. You don't have the same questions. Things are randomized, okay? I need to see the question you're actually working on and where you're at. So please send an email if you're having trouble, okay? I'm here to help you. If you're lost right now, like you're like, man, I get the math. But what is this saying? Ask me. I'm here to help you because like I said, on your final, it doesn't count for a lot, but it's enough to be annoying. I'm gonna ask you, you answered this question perfectly. But what does it mean? Like, what does this mean? What is this saying? This says 0.62. What does that mean? 0.62 of what? Well, it's it's a standard deviation of the sample they took from a population. That's a good enough answer, but it shows me that you're kind of understanding. Is that gonna help out a little bit? Okay. All right, guys, y'all have a great weekend. Careful, it may rain today, I guess. I don't know. You too, sir.